All right. So, things coming up. We have a mastering due tonight on Chapter 5 material. You have your group quiz today, also over Chapter 5. Your exam is October 27th, and it's going to cover Chapters 9, 10, 3, and 5. And we'll do an individual quiz on Monday, because we haven't had one in a long time. Why not? Yay! All right, let's see which pile of papers I want to start with. All right, so last time we finished, we were talking about naming. We just started naming a molecular compound. Here's ionic. This whole double-sided thing's throwing me for a loop. There we go. All right, so we had named the rules, the starting rule for naming a molecular compound. So we did nitrogen oxide. Okay, the second rule for molecular naming . So we're going to use the following prefixes to denote the number of atoms, right? So in nitrogen oxide, it was 1 and 1. But in NO2, you have to tell the reader there's 2 oxygens. Over here, I have to tell the reader there's 2 nitrogens, only 1 oxygen. So we're going to use the following prefixes, where if it's 1, we're going to use the prefix mono, or you can leave it off. Like in this case, it's nitrogen oxide. You could have called it mono-nitrogen monoxide. That would be fine also, but a lot of people leave that off. All right, so 2 is di, 3 is tri, 4 is tetra. Penta, so mono, di, tri, tetra, penta. Hexa. 7 has 2 options, both of which are fine, hepta or septa. Eight is octa. 9 is usually nana. Could be nano. And 10 is deca. You probably won't run into anything with more than 10. All right, so if, for example, we had that, right, so we had this guy. We had this guy. What should I call NO2 then using our prefixes and rules? Yeah, you can call it mono or you can just leave it off. That would be fine too. Nitrogen, and then there's 2 oxygens, so dioxide. Okay, how would I tell the reader that this is different than that one? What would I call this one then? Mm-hmm. And then what would I call the second half of it? Either monoxide or just oxide, both of which are fine. This would also be fine. So I think the naming rules for molecular are a little bit easier than the other one. Yeah, Justin.
So, okay, since it's mono and oxide starts with an O, why?
They usually just combine it. It would not be, again, it wouldn't be incorrect to have a double O, monoxide. I think just our language skills make it sound weird. So it's usually just monoxide. But for instance, what if I had, that guy. So Hg is what element? Mercury. So we call it, and then I have two iodines. Diiodide.
Wait, but that's spelled with what?
This one is spelled with two I's. But I would be fine if you did just one I, because the grammar rules are a little funky. I think it's because, like, if I have the prefix mon, it sounds the same as mono, like the word's still in there. But if I got rid of one of these I's, it'd be diiodide, which maybe doesn't tell you the same information as diiodide. So use your best judgment as to how many vowels to put in there. It's going to look weird regardless of which way you do it. Let's see, what if I had... What would I call that compound? Phosphorus. I never spell phosphorus right. Phosphor. Oh, there should be an R. Oh, yes, there we go. Bless you. I'm missing you in there also. Man, those U's. Phosphorus trifluoride. What if I had P4O6? Yeah, tetraphosphorus. Yep. And again, sometimes they put the A in and sometimes they don't because it's a double vowel. So sometimes it's that, sometimes it's again, that's weird, hexaoxide, or just hexoxide.
I think in the homework it takes
The A out, yeah.
Because whenever I tried to do it.
The AO, yeah. Yeah, it's weird. So probably just one vowel, unless it's a double I. Double I seem to be okay. What if I had I had boron trichloride. What elements, letters should I use? Okay, so B for boron, and then what letters for chloride? Cl, and then how many? Yep, three. Okay, what if I had tetraphosphorus decasulfide? So what letter would I use to represent the phosphorus? P, and then how many of them? Okay. What letter tells me about sulfides? S, and then how many of those? 10. All right, so then my challenge problem is
Sulfide doesn't have oxygen attached to it.
if it was sulfoxide, then it'd have an oxygen. It's just sulfide. All right, so what's the difference between ammonia and ammonium? Yeah, right. So which one of these two, number 1 and number 2, is the charged one? This one has a charge, this guy. And this guy does not. So if you don't off the top of your head know the difference between ammonia and ammonium, those are going to show up a lot in these molecular namings, just because it's the common name rather than the official name. Like this should be nitrogen trihydrogen, but we just call it ammonium. All right, any other questions about that? You guys feel pretty confident in your prefixes and suffixes? Until proven otherwise, right? All right. In that case, let me find my next sheet. It is a handy little table from your book that you can look at while I am looking. Don't worry about acids, just ionic and molecular. So if you're confused about which naming route to go down, if it's metal and non-metal, you follow the ionic naming rules. If it's two non-metals, you just use a prefix, element, plus the suffix IDE.
Is this in our textbook?
It is. It should be table, or figure, I guess 3.2 or 3.4, somewhere in there.
Okay, is it like on a separate sheet on your website?
It is. I mean, it's on a PowerPoint.
Okay.
If you can't find it in the textbook, then it's definitely on the PowerPoint. You can print that off. Justin?
Like with ammonia and ammonium, other than the chemical difference of one being charged and one not, what is the like difference in nature?
This one is an ion, which means it's going to participate in ionic bonds. This one's molecular, so it's not going to participate in ionic compounds. That's the biggest difference. All right, now I lost my place again. I did that too. Formula mass and moles. Again, this should be a little bit of review. Then we'll use a little bit of review to go forward and do some new stuff. All right, so the average mass of a molecule of a compound is what we call, right, the molecular mass. Oh, do you guys have calculators? You'll need calculators for the rest of the lecture. We're going to do some math. All right, so the molecular mass or the formula mass, interchangeable. All right, is the number of atoms in the first element times that its atomic mass, plus the number of atoms in the second element, plus its molecular mass. So we'll do one together, then I'll let you guys work on practice a few on your own. Let's say I have sodium chloride, and I want to figure out the molecular mass. Using my fancy formula, which you don't obviously have to use, where would I find the molecular mass of sodium? On the periodic table, is the top number, the bottom number? I'm inside the box. The bottom number. And so for sodium, I'm going to do some rounding, 22.99. And what units does that have? Either AMUs or the more useful unit, something per somethings. Grams per mole. And then we have 1 chloride, and it's 35.45. All right, so that would turn out to be 58.44. What would be the units of that? Still in grams per mole, yep.
So you pretty much adding the atomic weights together?
Yep. All right, we'll do one more together, then I'll give you some challenge ones. Some extra extra additions and multiplications. I think you guys are ready to handle it, even though it's Friday. All right, so if I had carbon dioxide, I would have 1 carbon times its atomic weight, which is 12.01 grams per mole, plus 2 oxygens, which is 15.99 grams per mole. Good. All right, so here, let me write out your 2 challenge questions. All right. So I'd like you to find the molar masses of those 2 compounds. Aspirin, which is C9H8O4, and disodium ammonium phosphate. Can everyone see the periodic table, or do I need to put a periodic table? The only thing we can't see now is sodium. And sodium's, oh, you already had it. You wrote down the previous problem. Fine. 22 point.
What is hydrogen?
1. Everybody ballpark in that range, depending on exactly which periodic table you're using. They may be rounded a little bit different. Because the one I have on here only has 2 decimal places. That one over there has 4 decimal places. So as long as you're in the right ballpark of values. All right, questions about that? Again, that's kind of review. All right. So,
On the test, if we're not, if we're like in the same
Ballpark, yes.
Ballpark for
You should be
the
fine.
stuff that has rates of decimal.
Yep. Be no problem. Oh, question, yes. Hey.
Sorry, this is a trivial question. For the mold thing, can we, because I've seen some information in the past, can we just write MOL instead of just the word mold? Would that be anything?
Oh, like if I was doing grams per mole, that'd be fine.
MOL.
Yeah, you can write just MOL. I usually include the E because it can get confusing because there's a bunch of different types of moles we talk about, right?
And there's, I mean, there's difference.
And there- Yeah, I usually write out the whole MOLE. But if you can keep straight what you're doing, then it is not wrong.
Okay.
But really, the units are more for you. Oh yeah, that chair's super broken. I keep trying to get them to fix it. There's like another super broken one in this range over here. That one. Yes, that one's super broken. You can't lean back on them too much because this back will snap off. So. I haven't seen anyone fall out yet, but it's coming. It's coming. All right, so molar mass that we just calculated is the mass in grams of 1 mole molecules, just like we had in the units. So for example, right, what did we just had? We had right, so we just had that, which has 100, ooh, that's decimal points, wrong spot. 181.5. All right, so it's that many grams per 1 mole. Right, which means if I have 6.022 times 10 to the 23rd molecules of aspirin, all right, it's all telling you the same information. If I have Avogadro's number of molecules, which is 1 mole, 1 mole would have a mass of 181.5 grams. So it's a way of using unit conversions. So since we've done unit conversions before, let's go ahead and jump to our unit conversion practice problems so then we can get ready to do some stoichiometry and predict products. Yay. People done balancing chemical equations before? We're working up to it. That's where we're headed. Because if you can balance the chemical equation and you know how much you put in, then you can predict how much will come out using unit conversions. You guys look super excited by that. It's amazing. It's amazing. It's like predicting the future. If you know what you put in, you can exactly predict what's coming out. Without like a crystal ball or like a magic 8 ball or anything. With just math. All right. So, since we've done problems like this before, I'm just going to let you loose on it. You can work with the people around you if you want moral support. But let's say you have 72.5 grams of C3H8O. Or a tricarbon octahydrogen monoxide. How many molecules of tricarbon octahydrogen monoxide would you then have? And as my handy dandy, I'm feeling generous today, I'll go ahead and tell you what the molar mass of that is. That is If you finish that, then you can do the second half of the problem. Yes.
Is the molar mass that little funny U symbol? It's like,
It is sometimes written like this. It's a big kind of scripty M. Yeah. Because that's what we use when we use like gas law stuff. The weird capital M. All right, so if I want to start the first half of the problem, what units am I starting in? Where do I want to end up? Moles. So, all right, I have 72.5 grams. What can I use to get out of grams and start moving to moles? That guy? Do I use it as is, or do I need to invert it? Okay. All right, what units would I now be in if I stopped right here? Moles. I want all the way to molecules, though. So what is my next step? Avogadro's number. Do I put the Avogadro's number on top or on bottom? Top. Let's see what that turns out to be. How many significant figures do I get to have in my final answer? 3. I'll go ahead and round. What units is that now in? Okay, that's molecules. All right, that part should look familiar, right, that part? All right, second part is how many carbon atoms are in that many molecules. So, if I have C3H, all right, so I have one molecule of that. How many carbons are in that? 3. How many hydrogens? How many oxygens? 1. So within one molecule, I have 3 of these. So if I have that many molecules of this, how do I figure out how many carbon atoms are in this pile? Multiply by 3. And I'm going to show it officially as a unit conversion, just so that you can follow the units, but you would just multiply by 3. Good? Questions about that? That's like sort of review with a little twist.
So, is that, like, if we define how many hydrogens are in there, is it like how many oxygens are there? Is that supposed to equal a specific total? So it doesn't have to?
No, it's not like a fraction. It's saying like, in this room there are 20 people. I could count, how many people are wearing blue shirts, how many people. It doesn't work out the same as a fraction. So, yes, Sarah.
How is it that there's more carbon atoms than there are?
Excellent question. So, you think about this in terms of this molecule is the house. Right, if you think about a house, this molecule is the entire house. If it's a brick house, is there just one brick to make up the entire house, or is there like 1,000 bricks to make up the entire house? right? There's 1,000 bricks that make up one house. So if I wanted to count bricks, it would be 1,000. But if I wanted to count houses, it'd be just one.
Oh.
Right? So this molecule is the entire thing all put together. But it requires 3 carbons plus 8 hydrogens plus 1 oxygen to put it all together. So the individual amounts have to be more than the one thing.
So if we're thinking about it like that, like question 1 would be like the brick.
Question 1's the house.
Oh.
Question 2's the bricks.
Okay, wait, no, that makes
Yeah, yeah?
sense.
Or you think about like a car, right? A car has to have 4 wheels. So for every one car, it's 4 wheels. So if I had 2 cars, it'd be 8 wheels, even though it's only 2 vehicles. I need 8 wheels to get everybody going. So atoms have to be more than molecules. Does that make sense? Maybe, okay. There will always be more atoms than molecules. That's a good rule of thumb. I guess you could write that down. Actually, pretty brilliant. Go ahead and write that down. Yeah, there will always be more atoms than molecules, because the atoms are the thing that make up the molecule. Because atoms are elements, right? Just elements. And as you put elements together to make molecules, you have to have lots of little things to make the big thing. Ready for some more brilliance? I think you're ready for some more brilliance. All right, we'll do this, then I'll make sure you have enough time for your quiz today. All right, so the chemical formula can also give some extra additional information. All right, if you know the formula along with the molecular weight, we can figure out how many elements or how many atoms are in that compound. That's on the next slide. So we have this new thing called mass percent. So the mass percent is an individual element's percentage So before, right, I had individual atoms, so it was like 7 times 10 to the 24th atoms of carbon in the whole thing. But I could turn that into a percentage, right? So there was whatever the actual mass is, carbon contributes some, hydrogen contributes some, oxygen contributes some. And so you could figure out how much everybody contributes to the overall mass. So generically, mass percent of whatever element you want to choose, X, the X-Men element. It's going to be the mass of X in 1 mole of the compound divided by whatever 1 mole actually weighs. This will make more sense here in like 3 seconds when we do a practice problem. All right. There we go. Acetic acid, which is my go-to compound, I love acetic acid, is an active ingredient in vinegar. I would like to figure out the mass percent of the carbons, mass percent of hydrogens, and mass percent of oxygens in acetic acid. So, in order to use my fancy, super fancy equation, how do I figure out the mass of 1 mole of acetic acid is? right? I just add up all the masses. So the molar mass of CH3COOH would be, what, 2 times 12 plus 4 times 1 plus 2 oxygens. Yeah, it turns out to be like 60-ish. Or exactly 60. There's some water, maybe. All right. So now we're ready to figure out the mass percent. We'll do mass percent of carbon first. All right, so here I have CH3COOH. How many carbons are in there? 2. What is the mass of the carbon? So how much should the carbons weigh altogether in this thing? 24-ish, yeah. 2 times 12.0. All right, so 2 carbons, each with a mass of 12, over the entire mass. How do I turn it into a percentage? Right, because it's a fraction, then times 100% times. So in acetic acid, 40% of that mass is carbon, which makes sense, right? Because if it weighs 24, the whole thing weighs 60, that's almost half. Okay. We'll do the hydrogens. Right, so we have 4 times 1 divided by 60 times 100%. Bless you. So hydrogens contribute 6.67%. How would I go about figuring out what the last percentage is? 2 different ways. I could do that again, or subtract from 100. Yeah. What is that? 100 minus 40 minus 0.67. Good? Feel good about that? All right. Monday, we will take this to the next level and start using chemical formulas. Yeah. So you will need a calculator for the quiz, so don't put away your calculator.